Chapter 7 and 8 Notes, Ionic and Covalent Bonding. Our goal is to understand the difference between ionic bonding, which is a transfer of electrons, and covalent bonding, which is a sharing of electrons. The bonding impacts the behavior of elements and compounds. So how atoms are connected to each other gives us some of the properties that are going to be important to understand. So graphite and diamonds are both made of carbon. And graphite, your pencil lead, is not actually lead, it's carbon, is used as a lubricant for locks. And as a lubricant, it will allow that lock to work very smoothly. And diamond is one of the hardest substances that is known to man. And they oftentimes use that in industrial cutting operations. So if you need to bore through a mountain, they'll put a diamond tip blade and they will go through that mountain to cut through the rock in order to put roads through, or railroads. Both of them are simply pure carbon, and the only difference is how those carbon atoms are attached to each other, or what we technically call in chemistry how they are bonded to each other. They're both covalent bonds, and as a covalent bond, we're going to take a quick look at an illustration here that will show the different type of bonding. So in this illustration, I'll choose a central carbon atom, in other words, one that's in the middle, not on the edge. And in diamond, there are 1, 2, 3, 4 attachments for each carbon atom that is not on the outside. And if I look at graphite, graphite also has a carbon that's interior, but it only has 3 attachments. And as a result, diamond forms what we call a lattice structure that allows it to have properties of reflection, refraction that make it a beautiful diamond. And graphite, on the other hand, is useful as a lubricant because it has layers. This layer is very loosely attracted to the other layer, and so it works as a lubricant. But also, when you think of putting a pencil down on paper, one of these sheets will just slide off and be left on the paper. That's why it is possible also to erase it. So the bonding is going to determine a little bit about the properties of the substance and chemical bonding and structure are key to how chemical reactions occur. So our understanding of bonding is going to help us to understand why chemical reactions happen. So the types of chemical bonds. To learn about ionic and covalent bonds, we want to explain how they are formed. So we're also going to learn about something called a polar covalent bond in this section. So bond energy, we put energy in to break bonds, and we get energy out when bonds are formed. So you may have heard of an ice pack or a hot pack that athletes sometimes will use. And what happens is you break something, and in that little bag there is a combination typically of water and something else, and that is going to give you a cooling sensation. That cooling sensation means that you're putting energy in and getting more energy going in than is coming out. So they use an ionic compound in that in order to absorb heat energy. Bonds define the type of compound. So an ionic compound forms when electrons are transferred. And we will do a worksheet on this later on. And we say that it is ionic because metals form positive ions. They lose electrons. and nonmetals are going to gain electrons. And in fact, we can make predictions based on the periodic table. So let's take a look at our periodic table here. And we know that the periodic table is going to be divided into a few parts. In green, I have highlighted the metalloids, and the metalloids divide the metals to the left and the nonmetals to the right. For the nonmetals, we can see that everything in column 1 will form a +1 ion. Those are called cations. Positive ions are called cations. In the second column, we have a +2 ion, and then we have +3, but we avoid the metalloids, and that's going to apply basically to aluminum and gallium. So aluminum and gallium will be our two +3 ions. So once we cross the border of the metalloids, on the right-hand side, nonmetals gain electrons, and those nonmetals are called anions. Anions are going to take a certain number of electrons all the time. So nitrogen and phosphorus are always going to gain 3 electrons, oxygen and sulfur gain 2, and then the halogens, fluorine, chlorine, bromine, and iodine, will always have a -1 charge. So that is something that you should memorize and be able to use. So covalent bonds are different than ionic bonds. In covalent bonds, we share electrons. And this happens between 2 or more nonmetals. And the nonmetals do not want to join together by transferring electrons, but simply by sharing them. So when we look at ionic compounds, metals and nonmetals combine. When we look at covalent bonds, that is 2 or more nonmetals. There's no bond between different metals. So if I were to put together some copper and iron, that does not form a bond. It forms what is known as a mixture, and technically it is called an alloy. So let's do a quick example of ionic bonding and covalent bonding. So sodium and chlorine, that is sodium a metal, chlorine a nonmetal, are going to form an ionic compound, because that is the combination of the metal and the nonmetal. So I got to go to my periodic table, and I see that the number of valence electrons that sodium has, sodium is here on the periodic table, sodium has 1 valence electron, and chlorine has 7. So to demonstrate the type of bonding that goes on, I'm going to use what's known as a dot structure. And I'm going to use a dot to represent an electron. So sodium transfers an electron to chlorine. This leaves sodium with a +1 charge because it has more protons than electrons. Chlorine has a -1 charge because it has gained an electron. The formula of that compound is NaCl. The positives and the negatives will cancel out. You will notice that sometimes a 1 is put on the positive or negative. When it exceeds 1, we always need to put by how many. So let's take a look at strontium and bromine. When they form an ionic compound, we have strontium, and I believe strontium is right there on the, oops, I'm sorry, that's incorrect. Strontium is going to be over here on the periodic table, and I did it with bromine. So bromine is there. Strontium 2 valence electrons, bromine with 7 valence electrons. And I'm going to put my 2 dots. And for bromine, I have 7. So the goal of every metal is to give away all its valence electrons. So metals give away all valence electrons, but they just can't hang out there in space. They have to go someplace very specific. So strontium has to give away 2, and it is going to go here on the bromine so that the nonmetal has 8 electrons with the transfer. So now we've got a problem. Bromine has 8 electrons, but strontium still has another valence electron. So as a result of this, we need to bring along another bromine with 7 valence electrons to take up that extra electron that strontium has yet to give away. When that happens, strontium now has a +2 charge. It is a stable ion, and we have 2 bromines. Each have gained 1 electron, but there are 2 of them, so we show it like this. When that compound's formula is shown, this coefficient becomes the subscript. So SrBr2 would be the correct formula for that ionic compound. When we have covalent bonding is going to be a sharing of electrons. So let's go back to our periodic table and find chlorine again. Chlorine has 7 valence electrons. And here's where covalent bonding is going to show a difference from ionic bonding. We have chlorine with Cl2 because it's one of the diatomic elements. And each of these chlorines has 7 valence electrons. So they're going to be connected by a bond. And a bond, which is that straight line, is equal to 2 electrons. This is, technically speaking, what holds the 2 chlorines together. The nuclei of each chlorine attracts those 2 shared electrons. So in a sense, each chlorine thinks it has 8 electrons. So for this chlorine, I have 2, 4, 6, 8 electrons. And the chlorines don't realize that they're sharing. So this chlorine also thinks that it has 2, 4, 6, 8 electrons. That number 8 is a stable number, and we call it an octet of electrons. And an octet of electrons in covalent bonding is the most stable number of electrons that an element can have. There is one exception, and that is hydrogen only wants 2 electrons on it. So one bond to a hydrogen is all it ever gets, because though that bond represents 2 electrons. So in summary, there are 2 basic types of bonding. Ionic bonding is complete electron transfer, and when we do that, we create ions. Positive ions are called cations. Negative ions are called anions. Covalent bonding is electron sharing. And if they share electrons equally, H and H, because they're both hydrogens, share them equally, that is called pure covalent sharing. If they share those unequally, and unequal sharing is going to be the result of an electronegative element taking more of their fair share. So if you recall, we looked at the trends in electronegativity, and as you go up and to the right, electronegativity increases. And when we talk about fluorine, fluorine is going to be the most electronegative element because the noble gases do not bond. They are not counted in for electronegativity. So fluorine is going to be the most electronegative element, and as a result of that, the electrons between the hydrogen and the fluorine are going to be shared unequally, and fluorine is going to get more of those electrons than hydrogen. This leaves hydrogen a little positive, and the way we show that is we use a Greek letter delta. This is the lowercase delta, not the uppercase delta like you're accustomed to, but we say that it's partially positive, and fluorine is going to have a slightly negative charge. That means it's polar, and polar simply means that there's a positive pole and a negative pole. So like the Earth has a north pole and a south pole, a polar molecule has a positive pole of charge and a negative pole of charge. So here's a couple of diagrams that shows a little bit about the electron sharing. A is pure covalent. Okay, so a polar pure covalent, equal sharing of electrons. This is hydrogen and hydrogen, and that little bean shape that you see is the cloud of electrons. So the bond is being equally shared between the two hydrogens. When we get to a polar covalent bond, so this is going to be polar covalent. This would be like HF, and in polar covalent, we see that the hydrogen has a delta positive and the delta negative of the fluorine. That's because fluorine is more electronegative and is grabbing an unequal share of the electrons that are in the bond. So it's not shared in the middle. Those electrons tend more toward the side of the fluorine. And then finally we have what would be known as ionic bonding here. And what happens is sodium would take part of, or that part of the molecule would have a positive charge, and chlorine would have a negative charge because sodium has transferred an electron over to the chlorine. So this is just the introduction to how bonding works, and I'm sorry I forgot to fill in this blank here, but a polar covalent bond represents a distribution demonstrating unequal sharing of the electron. Not electron transfer, a full positive and negative, but only a partial sharing.